So I'd like to welcome our speaker today, who is Shaheen Lakfabadi. He is joining us from Ryerson University today, so thanks for taking the cold walk over here. So Shaheen received his BEng degree in electrical and computer engineering from Ryerson University in 1998, and his MSc degree in computer systems engineering from Ryerson in 2011. From 1998 to 2009, he worked as a design consultant for various companies, including IBM, Honeywell, and MKS Instruments, designing both ASICs and FPGA designs. He is currently a PhD candidate in the Department of Physics at Ryerson University, and his research interests include biosensor design, near-infrared spectroscopy, optoelectronics, and optical coherence tomography. And today he's going to talk to us about extremely low-power FPGAs and biomedical applications. So welcome.
Thank you. Thanks for coming here today. This is a part of basically my research for my master thesis, but at the same time we published a journal paper on the research that I did, basically targeting FPGAs for biomedical applications. So that was basically the motivation that we did this research. I'll go through the agenda. We're going to talk about objective. We're going to talk about autoregressive modeling, which is a signal processing modeling that we targeted for biomedical applications. Overview of the FPGA implementation, how basically we used an algorithm, a Burg algorithm, which is one of the methods that you can implement autoregressive modeling. And then we dive into subthreshold circuit design to reduce the power of the FPGA that we designed. I'm going to talk about conclusion that we basically the result of the research and future work, future directions. So basically, collecting biomedical signals, well, biomedical business, basically biomedical research is booming these days. And there are a lot of research around processing biomedical signal. And biosignals are basically any part of any organism can generate signals that can be detected. So we basically researched and find out that most of the biomedical signal processing happen on processors of some kind. And we thought that, okay, let's think about how we can implement FPGA. They were not at the time a lot of research on FPGA implementations. So one of the requirements, obviously in processing biomedical application is low power design requirement. The reason for that is there are a number of handheld devices that processes biomedical application. And for example, a hearing aid or some of the products that they are surgically implanted. These are all type of products that they're basically require low power design. And subthreshold circuit design was a good candidate basically to use for implementing a device that can consume less power. So this is, I'm trying to give you a general picture of what this design was all about, because there are a number of stages that we did different approaches. So on FPGA, basically, the big part of it, there are some, I will show you later, a kind of logic design, RTL part of the design as well, but basically this design, the requirements from biomedical signal processing point of view, it required an adaptive segmentation and AR model. I'm not going to talk about adaptive segmentation. That's basically chopping off the signals into pieces so it can be organized into different frequency boundaries which can be processed later. Well, what is important is AR modeling. I'm going to talk about this a little bit more because that's the tool they use to extract information out of the signals. That's basically the general overview. The AR modeling basically once the signals are stationary, converted from non-stationary to stationary through adaptive segmentation, then it passed through the AR modeling for generating coefficient and basically the feature extraction. So let's go back and see what kind of signals we're dealing with here. So the bandwidth of biomedical signals are kind of limited into a few tens to few thousand hertz. So this is a little bit wider than the audio signals. So from both ends. So they can't go more than 20 kilohertz, they can go less than 20 hertz, so basically is the audio range. That's why the AR modeling was considered for processing the signal, because this AR modeling was used in the past frequently for processing audio signals. So, as I mentioned, biomedical signals, they have basically a root from organisms, from different body parts that can generate a signal, but they sit in the same range of frequency, very low frequency range, which is a little bit different approach, because nowadays all the companies and researchers, they try to work on faster and faster frequencies, but we found that the cross-section that is very popular, and there are very interesting signals out there that they're not really fast, but they need low power design, basically. So, as I mentioned, we need to generate some parameters that we can correlate to the source of the change, for example, in frequency or amplitude, or whatever the source of that is, which is a physiological source. And that was basically the motivation in knowing what biomedical signals or biosignals are. Now, this AR modeling, if you search on ARMA, AR modeling moving average, this is widely used for audio signals. It is very well known and very well researched area. AR modeling is kind of, we are using Burg algorithm. It's along the same path, a different algorithm. However, what the objective of this algorithm is to generate some coefficients, that those coefficients can be correlated to physiological change. We have targeted this basically signal, any type of signal could be processed. We specifically worked on vibroarthrographs, which is the signal comes from the knee, but it could be used for audio signal. It could be used for ECG. Still, the feature extraction can be applied based on the coefficient of this filter. One significant thing about the AR modeling is that biomedical signal, sometimes we don't have the source of the signal, so we try to predict it based on, as is mentioned here, based on the value of current output, and predict, basically prediction of what the source of the signal is. And that obviously generates an error, which is the calculations of the error is the start of the generating the algorithm. So we want to know how far the predictions are from the actual signal. That's basically in Burg algorithm. It uses the minimum least square of the forward and backward prediction. And I'm going to explain a little while that what is the forward and backward prediction errors. So these are the formula. I don't want to zoom in too much into this, but basically the gamma of m is what we call that reflection coefficient. So the forward and backward, previous forward and backward coefficient, and next forward and backward coefficient, they are related through the reflection coefficient. I will show, well, based on that, based on forward and backward reflection coefficient, we find the solution of the filter, basically the coefficient that we are trying to correlate to physiological source.
Could you explain what are the forward and backward coefficients? I understand you're finding a bunch of coefficients, but what makes some of them forward and some backward?
Okay, let me go to the next. Okay, so basically, this was a part of defining the error between predicted signal and the excuse me, and the actual signal. So forward and backward prediction error, basically, those helps in the equation. If I go back, you will see how the error basically estimated based on that, based on forward and backward coefficients. So ultimately, the matrix operation that you see on the top, that's basically the matrix that's generated depends on how long the data is. It increases depending on the number of samples. And that is basically the solution that can be correlated to the source of the signal. So from hardware perspective, I'm a hardware guy, so from hardware perspective, I just want to know all of these formulas that I showed in previous slide and this matrix, how I can implement it. And I came up with a very cumbersome diagram, how many multiplication, division, accumulation this process requires. And maybe that was one of the reasons that people decided to implement this on a processor. Although it may take longer time, but because of the low frequency nature of the signals, that may be the microprocessor is a better solution for that. And nevertheless, in today's technology, today's FPGAs that we have, we're capable of handling this, and we did it. We implemented. It wasn't too much of the issue. It was the matter of coming up with a design basically. So my predecessor was working on this, and she went down to the road of using the Simulink and system gen. I guess you're familiar with it, to convert the Simulink into FPGA. So as we know, what system gen does, well, this is back 4 years ago. Probably they have improved it. But this basically is structural design. So it picks up modules and plugs it in. That's how Simulink does it. It's Simulink to FPGA does it. So the problem with that design was because this is an iterative process, she could not fit that more than 3 stages of that filter. So she could only fit a filter on order of 3 into an FPGA test. But obviously, we have a better solution for that. So the first thing that I did, I redesigned this so that we could implement further filters by any order, pretty much. So next slide, basically this shows one of the blocks of previous slide. So the first block is stage 1. It shows what is going on in there. And these are all comes from Xilinx ISE. So basically, it puts the blocks together, flip-flops and registers, and structurally designs the filter. So because of the feedback, the more we progress, the more stages and more logic levels we're going to have. That's why it kind of makes it impossible. Although she targeted the Xilinx Pro, the chip that she targeted, I also targeted the same chip to match apple to apple. Although we had better chips. We had, I keep thinking of Stratix, but guys help me out here. What is the?
Vertex?
Vertex. Vertex 2 Pro. So we had a Vertex 5 at the time, but I mapped it into the same chip to match apple to apple, basically. So this is a design that I came up with. There is nothing really special about it. It is a sequential system that probably all of you can design as good as I did. There's nothing special about it. I just, instead of structural design, I designed a data flow, adding a state machine that controls different registers, and implemented a VHDL and basically targeted the same chip. So the result was interesting because using that technique, basically, you see the first line is previous design. So that's simulating the FPGA. Order of 3, they used 18% of the flip-flops, 20% of lookup tables, 25% of the upright slices, and so on. 32% of the multipliers. So the recess of the chip was basically consumed heavily. Then when I changed it for the order of 3, I pretty much reduced everything by a significant factor. But what is more important was when I switched to 32, basically order, I still use pretty much the same resources. So that was the optimized design. Our point was to basically tighten the screws and optimize the design, and then figure out how much power we need for it. That was the point. So this design told us that, okay, we're in good hand, now we can measure the power. As we did. We used the same resources from Xilinx ISE to measure the power. But one other thing was important was, depending on the number of samples, because the design was optimized, so it would add to the timing of the total timing of the process. So I kind of came up with some measurement, depends on number of samples that we had and what type of an order of the filter that we used. Number of cycles I calculated. So we would be in good hand understanding when it comes to optimum frequency. The data that we received from hospital, the signal, knee signal that we received, it was maximum 8,000 samples. And then I'm saying maximum 8,000 samples, there were 8,000 samples per window. Remember at the beginning I said that we used that segmentation, so the segmented data was 8,000 at a time. So the maximum, basically, worst case design, in this case, we needed about 760,000 cycles, which from that simple calculation showed us that we need 2 megahertz clock frequency that we can basically process this. One of the reasons that we use, another reason that we use this algorithm was because this is computationally intensive algorithm. So much of the algorithm that they're out because it has that iteration in it. So it was a good candidate for measuring the frequency and power. I understand that this depends on what algorithm you have, how many cycles it takes, what chip you're targeting. But our point was to come up with a frequency that we can measure all biomedical signals with a popular filtering method that can be implemented on an FPGA. So 2 megahertz was good, but there was a problem. The problem was every paper that I looked at, they used subthreshold circuit. They could not achieve this frequency. So the frequencies in subthreshold circuits are usually less than 1 meg. So we had a little problem. We had a little fix them. We needed a little fix in there to go to 2 megahertz range. Next slide, the other problem was basically I plugged in 32-bit floating point implementation of the same filter and 64-bit floating point implementation of the same. And I noticed that, well, where you see the 2 lines are separated, that's basically the dynamic power consumption. But the straight line on the left, which is pretty steady, that is the static. So no matter what, when you turn on the chip, you have to be ready to spend that much power. So that's the problem. That's where we actually, this area we focus to reduce this, because that's actually the sharper slope and most of the power that's being consumed. And that was another reason that we consider subthreshold circuit to reduce the power needs. So we came up with a model of the routing of the basically routing channel of the FPGA. Comes from Dr. Betts and Dr. Rowe's book. We refer to that and model that. The only difference, which is not a difference actually, we figured out that instead of logic blocks, we use a load. We consider logic block as a load. So the point was simulating from point A to point B, transfer of the signals. So what happened in logic blocks, this way we kind of isolated from the routing packet. We just want to see that if we can generate its clock frequency of 2 megahertz and transfer the signal from point A to point B. But to come up with the metrics for this design, we had to come up with some numbers. And thanks to PTM and IFAR, we could come up with the numbers that I needed for simulation. So from the IFAR information, we came up with the geometry of the chip, and we estimated this size of the routing channel that we needed. And then PTM helped us, we implemented this on 32 nanometer technology back then, which was not implemented yet. So we used PTM. I don't know if you're familiar with PTM. It's a site from University of Arizona. And they are predictive technology model. We're basically predicting what is the future of technology. So based on that model and the metrics, the parameters that they took from these 2 sites, I was able to simulate. So obviously, the first simulation wasn't successful. Based on the, you go back, these models using the 4x buffers, multistage buffers at the beginning of the line and end, using the same old style CMOS transistor, I could not get the signals true. So it was basically noisy. It wasn't actually responding at all. Basically, the signal would die down in the middle. That was basically the motivation to see, first of all, considering subthreshold circuit, and then what we can do to improve it for this specific application. So subthreshold circuit, basically, what we know about that is the transistors that leak the small current even when they're in off state. So basically the threshold voltage is the voltage, the minimum voltage requirements for a channel, an inversion channel form, so that we have the current going through from source to drain. I was basically, I understand that most people in the room, they understand the basics of the CMOS. That's why I didn't include it into the presentation. So I hope we're on the same page. But in subthreshold region, basically, the current drops exponentially as the voltage falls below VT. So we call that weak inversion. That's one understanding that helps me in this design. And then obviously that can be used to lower the power. When we use VT as a source voltage, basically that reduces the total power. However, that has impact on the performance, obviously. So another thing that I want to talk about is body effect. So we know, like theoretically, we consider the transistor, the CMOS transistor, as a three-port, or basically three-port, three-terminal device. However, it has a four-terminal. Okay, the fourth terminal is body, but in older style design, basically we connect that so that there is no leakage current, because leakage current is undesired for us. However, we'll see that in this design, actually the leakage current helps us to improve the performance. So the formula for threshold voltage is presented. VT0 is when source and substrate, they are at the same voltage. A simplified version of the formula is given in 1.8, which is basically we consider phi and gamma into k of gamma, which is basically, we call it body effect coefficient. As you say, it's a linear kind of equation. And there are two possibilities, two options for biasing the transistor. So having a V source to body. One is reverse bias, the old style that pretty much used in many, many chips. That actually increases the VT and then reduces the leakage power. And the other option is forward biasing that, so applying a voltage so that it decreases the VT and increases the device performance. So this is basically a conventional NMOS, the way that we used to use that. As you see, between substrate and source and substrate and the drain, there are p-n junction, there are diodes, which we used to reverse bias them so that there would be no current going through those diodes. Only in the induced N channel, for example, P channel, basically the current would flow. However, for this design, we realized that because we need, well, first of all, V threshold voltage is our power source. Okay, and using this topology, that does not give us enough current to speed up the transistor so that we can hit that 2 megahertz frequency. In order to improve that, so this is basically, if we apply VT in here, and that's how, when I say the frequency is maximum about 1 meg and less, it cannot, because it cannot do, you cannot run the circuit better than that clock circuit. Now, in order to increase that, basically I came up with the idea of switching body bias technique. So this picture shows you the inverter on the left is conventional inverter. As you see, the body is, for the P channel is connected to VDD, and for N channel and for N transistor is connected to the ground. So the reverse bias mode. for the body to source and body to the gate to the drain PN junction. So when I use this technology, which is swap body biasing, or some paper they call it switch body biasing, as you see, I reversed this. So basically, I connect the P channel to the ground and N channel to the VDD, so that the leakage current start flowing. And that leakage current helped me to go through that rotting channel with no problem at 2 megahertz. So that was the improvement over previous, basically, methods. However, yes?
I have a question about that. So
Sure.
at VDD, for example, on the NMOS transistor, how did you forward bias the junctions, and your diodes are now drawing a huge amount of power? You have, so the NMOS device, you have an N source, an N drain.
Yes.
And you have a P well or a P body.
Yeah.
So you've put the P at VDD, your source is at ground. So I don't know what your VDD is, maybe 1 volt, or is your VDD very small?
VDD is very small because VDD is VT. So
Okay.
we are using threshold voltage, that's sub-threshold circuit still.
So how high can you take that VDD before you significantly forward bias the diode?
In my experience was about 0.65 volts. I have the diagram. I actually basically scanned that through to see where is the optimum point. And 0.65 was where the system wouldn't work anymore.
Because the diodes are forward biased?
Yes.
It's drawing huge current?
Yes.
Just make sure I understand this, how this is working. So you're applying an almost, what's the term again for the minimum voltage for a diode, the forward biasing?
Yeah, the built-in voltage.
The built-in voltage, you're applying almost that, so you're reducing the natural depletion around the drain gate and the body, and that makes it easier to create a channel,
Well,
so you can operate better at a lower
if you
threshold voltage.
look at the diagram on the left, basically let's consider the P. So the P transistor right now, the voltage applied to the gate, and then the body is basically connected to VDD. So there is no voltage difference. Let's say the voltage difference actually is backward, so that's why the diode basically is backward. So electrons in P channel, electrons going backward.
I know, it's
So
reverse
there's no
biased, so there'll be a depletion area.
Um,
around it. So if I
It's
understand-
not, it is a depletion
Region, yeah.
region. However, it is not same as strong between source and drain.
Mm.
Okay? If you actually look at, zoom in into that area, the current is not going to streamline. Its current is kind of flowing in all directions. The electrons flowing to all directions. So basically, the geometry of that is not exactly like a channel that we have from source to drain.
Okay, yeah, it's all over. I'm just asking, is the reduction of that depletion zone the reason why it becomes easier to create a better channel when you're doing swap body biasing?
No, it's not.
No?
It's the gamma effect, it's the body effect. So if you go back through your field equations, you have to work through it. Basically, you're making it easier to create the channel because it's all about bending the valence band enough that you can move. So you have to draw the band diagram, but effectively,
Okay.
by putting a voltage on the body, you make it easier to bend your bands enough to create the channel.
Okay.
And then, I don't think I could, you could do the math to show that.
I got the rough idea, okay. All right.
Right. So
It's got nothing to do with moving carriers, basically, or proportions of carriers.
It does. Makes it easier to invert the channel, which creates carriers.
Well, yeah. All right, then, all right, then. Okay.
So for multistage buffer, which is basically the driving force at the beginning of the route, and what is taking the signal at the end, I came up with this architecture. Now, I'm quite sure now some people are going to ask me that why not 2 of those? Well, 2 of these, obviously, the conventional method obviously didn't work. So this combination was the only combination that worked, because when I put two of the SPB buffers together, then the noise margin, it's killed the noise margin. The noise margin of the second stage was too narrow, then the signal wouldn't pass. The reason for that, I didn't investigate it. However, I guess that because it basically, it is true noise. It's not just, as I said, it's not straightforward current that same as a forward biased diode current that we can sit down and measure and put it in some exponential calculation. It affects the noise margin. How, I don't know. That was basically, I put it on my future work sheet to see what are the limits of putting two of these buffers together, and why it doesn't work, and how much that affects the noise margin. But this basically helped me to be able to simulate that routing path and successfully getting the signals true. So I came up with the metrics, basically conventional buffers on one side, the switch or swap quality bias buffers on the other side, and different voltage. The voltage of the star, I considered them as threshold, subthreshold region. So the optimum point was 0.4 volts for threshold voltage. Basically, as you see, the buffer's delay became about 11 nanoseconds. So this is much more than conventional buffer in terms of a delay. But that was the optimal point, considering the power that we saved. So power delay product was evaluated at around the green basically zone. So, by the way, we consider 20 track the longest track inside the FPGA, and 20 tracks of the same routing lengths. So that was only a 20 nanosecond delay. So this is the diagram that I was referring to. I basically scanned at two different voltages, and to see that the conventional buffers in blue and the SPB buffers in red, how they behave. I mean, the optimum point was pretty much down in here between 3.5 and 0.4, and at around 6.5 is where the conventional buffers start showing more stability than the model that I considered, the switch bias body buffers. So basically that brought me to the conclusion. Using this technology, we came up with 197.7, about 200 times reduction in power. So that was huge. Although that's a little bit deceiving, better measurement is power delay product, which is 10.78, which is still significant. It is significant because you can consider that what we are considering are handheld devices and the life of the battery. And devices like, for example, pacemakers or hearing aid devices that can be implemented requires surgical operation to change battery. And the significance of this is, let's say, for example, a pacemaker person that has an initial heart attack at age 60, the life of the battery is usually 15 to 20 years. So 15 to 20 years later, when he's 80 years old or 75 years old, requires another surgical operation to change the battery. So basically this eliminates that second operation. Although I didn't kind of design for something like a pacemaker, but still the same technology could be used. But for hearing aids, the hearing aid devices that have been implanted, the same thing. It requires a surgical operation to change the battery after whatever the life of the battery is. So that basically eliminates that requirements. We also proved that we can use FPGAs for biomedical signal. We use the computational intensive algorithm we implemented on FPGA. We showed that we can, 2 megahertz frequency, we can come up with 2 megahertz and run that chip with that frequency and accomplish basically the design and come up basically with the, run the algorithm successfully. So also it proved that, well, this was proven. Other people, they have used subthreshold circuit for FPGAs. They actually not, we only use for the routing tracks. There are researchers that they have used for logic blocks, for memories. There are a number of researchers out there. They have proved that however, they still have that frequency limitation. They couldn't run that more than 1 megahertz. Not even 1 megahertz, less than 1 megahertz. So that's basically the conclusion that we came up with in this research. Now for the future work, obviously we need to consider logic blocks, block RAMs, functional units, multipliers, or other units that we have on the chip, and use the same architecture to see if that works. I did not have time to finish that. There are other body biasing types. This is not the only one. We use the fixed body biasing technique. So there are dynamic body biasing method that basically they connect the body to the input signal. So that way dynamically it adjusts. There are other techniques that also should be investigated for the FPGA fabric. They've been investigated for other designs, but not for FPGAs, at least I don't know. And we should also consider this for basic devices and see. One thing we really like to do was to implement this on an ASIC and see how much power we can save FPGA versus ASICs, which that obviously ASIC has different metrics for power consumption and doesn't require that initial, it doesn't require, but it doesn't require as much as FPGA static power. So those are basically what I think is good topics to investigate further in this area. And that's concluded my my work. Appreciate. I should actually acknowledge Andy Yu's work, which he was my supervisor. He was all involved in this project, especially in terms of initiating the ideas and in submitting the paper. He worked pretty much all the way through with me. I appreciate that work. Wombats and Jonathan Rose, we use the book, the purple book, a lot. Actually, in my thesis, I used it more frequently. I used the gate boosting, all of those ideas came from that book. I should appreciate University of Toronto for IFAR side, that was very helpful. And also VPR. That was basically inspiring, and we kind of followed the research here in many different perspectives. Also, nobody's here from University of Arizona. PTM side was very, very helpful as well.
Actually, the original subthreshold idea actually has come from, we had a discussion about that was way back when we were talking about that, so that's all.
Okay. So thank you very much.
Thank you.
For the application that you're dealing with, does it make sense to move from floating point to fixed point? Because I would expect for biomedical, you wouldn't have that large of a dynamic range.
Yes, there was another research on the same topic. I don't have a paper in my reference, and I didn't know how much I'm going to talk about AR, but they actually implemented this on a processor, and there was no significant difference between fixed point and floating point. So most of the work we did, we actually worked on fixed point, 32-bit fixed point. The error, or maybe I can say this, not even the error, the accuracy of the coefficient, resultant coefficient, was pretty much the same. So floating point really for this algorithm didn't do much.
What is the end application? So the idea is you would implant this, you do autocorrelation, you're building a model of the signal, and what a medical practitioner then do with that model of the signal that's being computed all the time?
Yes, the idea is basically this is a diagnostic tool. So we are giving more tools to physicians to understand what are the typical problems. We investigated this for knee signal specifically and knee injuries. So basically this algorithm and feature extraction can separate between different type of knee injuries because the signal frequency and then amplitude changes when any, for example, kneecap injury. So that was, it wasn't a part of my investigation, but my partners, they're still working at SARD at Ryerson on that topic.
So is the idea of doing it, I mean, I can see two ways to do that. You could do it with an implantable device that does the computations, or you could capture the data and send it wirelessly perhaps to something to offline compute. So is the idea of doing it in place that you can massively data reduce the data? Like,
yes, I'm glad that you asked that question because I forgot to talk about this. One of our motivation was basically this device should be connected to the patient for 24 hours, for example, or 48 hours, to collect a signals over time, and that requires a lot of memory if you do that on other, let's say, type of hardware. In order to reduce the memory size, this feature extraction, basically, instead of the entire signals, we just take the coefficient and store them. So that can be stored locally on a handheld device. That was one of the motivations to go after designing this, and especially low power design of that.
For essentially that sweet spot that you're putting the supply voltage in, that will be very sensitive to operating temperature, or?
Operating temperature of the transistors?
Yeah, well, I would expect the semiconductor behavior to change somewhat depending on the surrounding temperature. Right?
Yes.
And that would, I think, mean that you would have to adjust kind of like your sweet spot which you're operating for your supply, right?
Yes.
So I can't really quantify how much that would change over, like,
Yes.
or even if you have to assume a large temperature range, given that you're probably always close to the body.
Yes. One of the things that I did not research that, but I know that the problems and issues around this. One of the problems is that some other researchers, they designed a separate circuit for biasing that is adaptive. Basically, they do adaptive biasing. That's one solution because the temperature has an effect. Okay, so to adjust the temperature effect, let's say a part is inside the body, then temperature range is different, and that directly affects threshold voltage. So they have this tuning circuit on the side to adaptively fix the operating voltage.
Could you go to your, go ahead.
Oh, I was going to ask this question last because it's a little more far out than the other questions. I just wonder why it's necessary so much right now to be focused on reducing the power usage of implantable devices when the human body, even during its idle state right now, we're all generating and using like at least 100 watts just right now. With this huge untapped power source right here, and we're focusing on running things on batteries, it seems kind of silly.
Right.
We could easily spend like 10 watts, even something as astronomical like that, we could run something 24/7 off that if we
Yeah,
wanted to.
yeah, I'm with you on that topic. You know, I've seen movie metrics myself. But the point is, in biomedical application, one of the significant differences from other applications is reliability. So we're talking about human life. And then everything should be calculated down to cent and pennies. And there is no error, there is no room for error. At least no designer wants to be the designer of a battery or system that takes some energy from, it is true that you're saying that our body generates electricity, but that very depends on the DNA and could be very widely different from one person to another. So accountability and basically predictability on how much power and how is up for the research. I'm not saying it's not doable, but at this time, you know, in 21st century, this is the best that we can do. We have to rely on batteries.
Harvesting 10 watts from a body is a lot in terms of
Yes, that's a lot.
thermodynamics and
Yeah. Yeah.
Yeah, how do you want to
like
do
if
that?
you cover like all of your body, essentially it was like
That 100-watt
Something
figure is
crazy.
usually when you're like pedaling like crazy on a bike.
No,
But I don't.
That's idle.
like you're like just like maintaining
But
this.
it's heat, you need to have a big bucket of ice. near you and some kind of
I think Alex is thinking of like glucose fuel cell,
Yeah.
but I'm not sure which arteries would stimulate.
You can find one. It's near the heart, right? It's got plenty of blood.
Well, so reducing the power consumption via subthreshold operation is awesome. Like I'm really impressed by the results. But a silly question: has the alternative been considered? Since you're using an FPGA, and it takes milliseconds at most to configure, not a huge one, to simply run your design at normal circuitry at as low a speed as you need to, and or as high a threshold as you need to reduce leakage, and basically just turn it on, take your measurements, do your calculations, store it, turn it off, and then wait some period and then do it again.
Yeah.
Operate at normal rate, but at a low duty cycle,
Yeah.
or vice versa.
What you're suggesting actually has been researched. There are some FPGAs with a sleeping circuit. So it has a sleep circuit. It puts the chip into sleep after the operation done, and then you can crank it from outside or internally it can be. Nowadays with reconfigurable FPGAs, that's even easier. This doesn't really conflict that. However, they can be used side to side. It's still we can save the power in this method and that method.
Okay, I was just wondering if there was a comparison between, can you get the similar power gains from low duty cycle versus subthreshold?
That goes back to the number of cycles, how long you want to run. Remember I did that calculation? Then that would be application specific. So we have to make that measurement per application.
Doesn't that translate into wherever the minimum power delay product is, assuming
Yes.
you keep up with your design?
Yeah, yeah.
So,
That,
if you run faster, you run for less time.
Yeah.
The total energy is basically pick a point on that power delay product, which was lowest at the bottom left.
Are those equivalent? Like, do you have some sort of efficiency loss from running at subthreshold versus running high speed but low but high threshold?
Well, I would say it's basically captured in that plot, because the power delay product is energy, right? So that is, if you want to do a given amount of computation, you pick a point on that curve, and it is how much energy you took.
And that takes into account leakage and all that.
That'd be a good question.
So if you're running at high speed, you get less static but more dynamic, whereas the other way you get more dynamic, less static. Sorry, more
well,
static,
for
less
FPGA, the static's pretty much steady.
Yeah.
It doesn't change that much. I have the graph, actually, let me go back to that graph.
Yeah, I saw that.
Is little difference between number of cycles. See, it's little difference between using more resources. 64-bit obviously uses not double the resources, but it uses more resources. But you see that the static is not really that much.
See, that motivates it right there.
Yeah.
Because whether you go run at low speed or high speed, the difference in power is much less than your base static power consumption.
Yes.
So that means my idea of using low duty cycle would actually be less efficient than subthreshold.
But what I'm saying, the optimum impossible point is that we have a straight line in here, right? However, we still have to consume that much. That's we cannot, that was what we went after, to reduce that state power.
What percentage of total power was static, comparing your like subthreshold design with your non-subthreshold design?
I did not measure that really. That's a good point. Well, I did not measure that because I couldn't measure that. Because I did not have the chip to implement this circuit and see how much is the difference. That was the problem. Maybe Altera can help us to give us a chip with that architecture, and we can load it and see the difference.
So does it take $100 million?
I might just have missed it, but did you have like a final estimate number of what kind of milliwatt you would end up with for your RR32 example?
No, I don't, because that goes back to the same question. This chip is a hypothetical chip. We didn't have the chip to load it and extract the measurements.
I mean, I understand that, and also I/O and stuff like that, but you should be able to scale up from what kind of number of logic cells you use to like an estimate of how much.
Well,
power
on the
you
same,
actually have.
on the same track, we reduce the power delay product by a factor of 10. So that's significant, considering that most of the area of the FPGAs are the routing. I would say that's pretty much significant. Even if in other areas, let's say if 70% of a chip is routing resources, pretty much on that 70%, we reduce that by a factor of 10, which is significant. But
the thing is just, I could naively argue, and I probably would be wrong, well, let's take a fairly low power embedded processor and run the same thing as you've discussed in linear C code.
yes.
And I will get down to a few milliwatts to do that probably, for the kind of data throughput that you have. So it would be good to end up with some kind of ballpark number of where the FPGA actually takes us. I probably believe the FPGA on subthreshold can be the embedded processor, but it's hard to say without any.
Before I do this subthreshold, I did a little bit of research of what processors and DSPs we have in the market and what are the powers pretty much. The problem with processors is also they need a minimum requirement to turn on the chip. So that is still there, like you cannot reduce that. Now how fast you run that chip and how intensive is the computation, that changes the dynamic power on processors as well. But it's still, the minimum requirements for processors are there too. So I think that's why it makes this design valuable, because that reduces the minimum requirement. So that's basically is the idea.
You showed so you talked a lot about the routing buffers. Did you look at how to build the routing muxes at all? Or
Muxes?
yeah, the muxes in front of the buffer.
Yeah, muxes, I didn't show that here. I referred to the purple book again. I used the same structure as muxes in, let me go back to the, yeah, this muxes are actually use the same structure that used in the, are you familiar with it?
Yeah.
That cap, yeah. The gate boosting and all of those basically architecture pretty much is the same, except for the buffers.
Can you go to your table of results from the power delay product?
Table of results, the power delay.
That's, I think, there. There's a couple questions about this. So with the switch body bias, so this shows that your power is going up, but you're able to take it all the way to 0.9 volts, and it hasn't kind of gone blown up yet.
In here? Yeah. So,
Do you trust the predictive technology models at that point? Because usually with forward bias, people usually limit it to about 300 millivolts is typical to avoid getting significant current through the diode. And at 0.9, that diode is fully on. So I'm surprised basically that the power hasn't gone to close to infinity.
that's a very good point, but these are basically the simulation result that I was trying to scan through to find the optimum point. And then I started from 0.9, which is typical voltage used on the devices these days, and then going to subthreshold region and see what are the differences. As I said, the switch body biasing is not really a good candidate for higher voltages, and that's one of the reasons.
I guess another question, if you were able to change the threshold voltage, so say you have a hypothetical process where you could pick as many threshold voltages as you want, would you be able to get the same results? Now that process doesn't really exist, but let's say that it did, I'm just trying to understand the results. Could you get the same power reductions without switch body bias? Because you could pick any threshold you want for those transistors?
We might get the power delay product, but the problem was at that frequency it doesn't operate. Then I had to lower the frequency. My point was running at 2 megahertz. Yeah, if you go to lower 1 meg frequency, probably you can beat this. But that was the problem, the 2 megahertz requirement.
I want to get a better understanding of the numbers more. When you said that you had a 10x power delay product improvement, was it what was it with respect to?
To the routing channel.
Oh, so conventional non-subthreshold versus subthreshold.
Yes.
So that would imply that static power is, so the power consumed from, the energy consumed from dynamic transition is going to be constant for power delay product, because you're measuring total energy for operation.
Yes.
So the difference that we're seeing then is entirely due to static reduction?
It is a power delay product. We are also running at 2 megahertz, which is not a high frequency. So I don't know if we are measuring here apple to apple, but reducing the energy in total.
Because the energy total has 2 components. You have the dynamic power component times the total time that you've been switching.
Yes.
Plus the static power times the total time of your operation.
Yes.
So if you manage to drop it by 10x, the energy consumption from dynamic switching can't change, because I assume that the capacitance is about the same for both processing.
But the voltage is
Your voltage.
Oh, voltage drop. Okay, that's right. Okay, good.
Does that answer the question?
Any other questions? Okay, well, let's thank our speaker again. I'd like to thank Altera and Dave Galloway, the pizza representative, for the pizza. So he successfully signed his name, and let's congratulate him for that.